In this video, we're going to set the framework for generalized quantum scattering. We'll first start by looking at classical scattering, the differential cross-section. Then we'll talk about quantum scattering. And finally, the different approaches that we're going to take to solve scattering problems. So the generalized scattering problem starts with a particle moving towards a scattering center, which is here in red, and the particle has the blue trajectory. The initial direction of the particle is conventionally laid along the z-axis. B is called the impact parameter, and it's the perpendicular distance from the initial trajectory to the z-axis, that is, the axis that contains the scattering center. Theta is the scattering angle, and it's defined as the angular deviation from the initial, which is this dashed line here, to the final trajectory here. That angle is theta. We're going to assume that the scattering center is fixed, and then given the initial energy of the particle and the impact parameter, as well as the interaction forces between the scattering center and the particle, we want to calculate the scattering angle theta. So the output is the scattering angle theta. And this is classical scattering. Within this formalism, we also want to calculate the so-called differential cross-section, which is laid out in this figure here. We'll start by noting that the particles that are incident through an infinitesimal area d sigma are then scattered through a solid angle d omega, which is over here in red. D sigma is an area, and therefore it's given by an infinitesimal rectangle. The rectangle on one side is b d theta, which is b is the impact parameter, and theta and phi rather is the angle around the polar angle here around the z-axis. That's the length of this side, and then the length of the other side is just db. So you have d sigma is equals b d phi db. The solid angle on the outward scattering part, the scattering side, is equal to the area of this rectangle here in red divided by the radius from the scattering center squared. So because this is an area, you divide it by basically the radius to get the scattering solid angle. Radius squared scattering solid angle. And in this case, this rectangle has one side which is r sine theta d phi, and the other side is r d theta. So r sine theta is the perpendicular distance from the z-axis to the center of this rectangle, and then d phi is the angle times the polar angle. And then the other side is just r, which is the radius of the sphere, times d theta, which is the azimuth, the change in the azimuthal angle. And so you have d omega is r d theta times r sine theta d phi divided by r squared to make an angle. So this is an area and this is an angle. Well, clearly when we cancel the r squareds here, we get sine theta d phi for my solid angle d omega. The differential cross-section is defined as d of theta, which is d sigma over d omega. And we can just write down what this is. D sigma is b db times d phi. And here we have sine theta d phi, and we actually cancel out the d phis, and we're left with b over sine theta, which are constants, divided by the absolute value of db d theta. The total cross-section is the integral of the differential cross-section, and we call that sigma. So sigma is the integral of d theta integrated over the solid angle over an entire sphere. So this depends on the angle, and you have, and since there's a cylindrical symmetry here because of the z-axis, this only depends on theta, and this integrates over the entire sphere of that solid angle. We also can talk about a term called luminosity, which is defined as the number of incident particles per unit area per unit time, and that is what's telling you what's going through d sigma. And the number of particles incident through d sigma is then given by dn, which is the luminosity, which is the number of incident particles per unit area, times the area of that d sigma. So that gives you the number of total particles. And we can then rewrite this in terms of the differential cross-section, which is the luminosity times d of theta times d omega. And therefore, we have another definition for the differential cross-section, which is just equal to dn d omega, the number of particles coming through a solid angle d omega, divided by the luminosity. So that was classical scattering. For quantum scattering, we have to treat things a little bit differently. In quantum scattering, we want to treat the incident particles as plane waves because of the wave-particle duality. And so a plane wave for the incident particle is just given by, again, this is incident direction is z. So we have this same cylindrical, we have a plane wave coming in along the z-axis. So it's a e to the ikz. So it looks like a free particle that is a plane wave moving along the z-axis. That's psi of z. The scattered particles we want to treat as spherical waves. Let's assume that you have a scattering center, which is sort of a point source, and the scattering is spherically symmetric about that point source, and we can write that spherical wave as psi scattered of r, because now it's spherically symmetric, is equal to b e to the I kr over r. This, of course, is a spherical wave, where k is equal to the square root of 2me over h bar. And the k is the same because we're talking about elastic scattering. That is, the energy doesn't change. And so the wave vector doesn't change. It's just that it comes in as a plane wave and goes out as a spherical wave. So if you're very, very far away from the scattering center, then you know what the solutions must be. The solution must be a superposition of the incident wave plus the scattered wave. And so you can write the wave function at a far distance away from the scattering center as psi of r and theta is approximately equal to a, some normalization constant, times e to the ikz plus a scattering factor f of theta times e to the ikr over r, and that's a spherical wave. And the scattering factor theta, f of theta, is telling you how much of that incident wave is actually scattered. So it's a number that's less than 1, and it's a function of theta. So this is just a superposition of the incident and scattered waves. The differential cross-section, therefore, can be written as d of theta, which is d sigma d omega, and it turns out that that's what we have to calculate. So the task then is to calculate the scattering amplitude f of theta, which contains all the information about the probability of scattering in a particular direction and related to the differential cross-section. So let's imagine that we have our area d sigma, and we want to look at the probability that the incident particle passes through an area d sigma in a time dt. So that particle is moving with a velocity v, and so in a time dt, it moves a distance v dt. So any particle that starts out in a volume like this, which is v dt long and d sigma in area, will pass through the area d sigma in a time dt. And so we can calculate that the probability of those particles as the incident radiation, the incident wavelength, wave function, modulus squared, that's a probability density, times the volume, dv, of this figure that we have here. But that volume is simply v dt times the area d sigma, the cross-sectional area d sigma. And because psi incident is a plane wave, then all you have is your normalization constant a squared. because it was a e to the I kz. When you take that, the complex exponentials go away, you just get a squared. So this must also be equal to the probability that the particle scatters into the corresponding solid angle d omega. And we can calculate that by taking the scattered radiation, psi scattered, and taking the modulus squared of that times dv again. And in this case, you get a squared times f squared, the scattering factor, divided by r squared, times v dt times r squared d omega, because this gives us an area. So the area is r squared d omega, v dt is still the velocity of the particle in the time, and now you have that scattered radiation, which gives you that a squared f squared over r squared. That's the scattered radiation only, not the sum of the two. Because the scattered radiation, if you recall, is a spherical wave with a scattering factor f of theta and a normalization constant a. Therefore, we can now calculate the differential cross-section by realizing that d sigma, which is here, if you equate these two, these are both equal to dp, the vdt cancels, and the r squareds cancel, the a squareds cancel, and you're left with f and d sigma and d omega on the other side. So d sigma is equal to f modulus squared times d omega. And therefore the differential cross-section, d sigma over d omega, is simply the scattering factor squared, or the modulus of the scattering factor squared. So now we have a framework, but there are many different ways of doing the scattering problem. We're going to discuss 3 approaches to scattering problems that are slightly different, but that are appropriate for specific cases, and will give you a possibility to solve the scattering problem. The first one is called partial wave analysis, where we use spherical harmonics to calculate what the spherical scattering of these scattered waves are, the wave function for the scattered waves. Another way is to do phase shift analysis, where we basically look at the phase that a wave picks up coming into the scattering center, and then the phase that it picks up as it goes back out from the scattering center. And then finally, we'll start with the integral Schrödinger equation and generate a Born series using the Born approximation to calculate scattering factors.